Hello, my name is Florian from the Digital Health Center of the Hasso Plattner Institute in Potsdam, Germany, and I want to present to you today our contributions to the DisTEMIST shared task at the BioASQ workshop at CLEF 2022, named Spanish Biomedical Entity Linking with Pre-trained Transformers and Cross-lingual Candidate Retrieval. We submitted multiple runs in this shared task, and for Subtrack 1 entities, our best performing run got second place, and in Subtrack 2 for entity linking, we got the first place out of all submissions. And I want to talk now in a bit more detail about the methods and results for both subtracks, starting with Subtrack 1 entities. Here our approach is actually rather a standard approach and similar, I guess, to what many of the other teams have done. For pre-processing, we applied sentence splitting and tokenization with spaCy and transformed the span-based annotations to token-based IOB labels, which allowed us then to use the data with off-the-shelf named entity recognition models like one from Hugging Face. For training, we first took apart 20% of the documents from Subtrack 2 as a validation set, so as a kind of hold-out test set used internally. And then the remaining data was shuffled on the level of sentences and split 80-20 into training and dev sets. We initialized the Hugging Face token classification model with a Roberta weights trained on Spanish biomedical text and used a token classification head. The model had a number of hyperparameters that were tuned using grid search over learning rate schedule, warm-up ratio, weight decay, and label smoothing. And in the end, we applied some simple post-processing to remove some artifacts like multi-line entities, which did not occur in the training data, or trailing white space, which also affected the evaluation. This post-processing amounted to an increase of 1.2 percentage point in F1 score. And as you can see from all of our submitted runs, the best score was achieved by a combination of the Roberta model with the linear learning rate schedule and post-processing. A bit worse where it was a constant learning rate schedule. And then of course the versions without post-processing were consistently a bit worse. So yeah, that's our named entity recognition model. And this was then used as part of our submission to Subtrack 2 as a mention detection component in the overall entity linking system. So once we have extracted all the mentions from the raw input text, we want to find for each of these mentions the best SNOMED CT code. For this, we created two different dictionaries. The first dictionary was given as part of the challenge as the DisTEMIST gazetteer, consisting of 111,000 concepts with 147,000 aliases. So there are about 1-point-something aliases per concept, which is actually quite low if you consider that in biomedical entity linking, many concepts have a lot of different surface forms. So to get access to a larger variety of aliases, we looked into the UMLS. And from all of the 16.5 million aliases in the UMLS in all kinds of different languages, we retained only the ones that were present in the DisTEMIST gazetteer, so because only these concepts were relevant for evaluation, ending up with a dictionary of 2.4 million aliases. These dictionaries were then used in different candidate generation approaches that were combined in an ensemble and re-ranked to get the final results. And I will talk about all of the components in more detail now. So as the first very simple baseline, we used the TF-IDF vectorizer-based entity linking approach and used the implementation from spaCy, which is based on character 3grams. And we rebuild these indices from spaCy, which usually are only for English UMLS. We rebuild these indices for the DisTEMIST gazetteer. And once the TF-IDF scores are computed, we can, at inference time, just do a k-nearest neighbor search to find the best matching concepts based on one of their synonyms. And this yields, on the test set, an F1 score of 0.361, which also includes the named entity recognition. So without needing to solve entity recognition, assuming that the gold entities are given, which we could compute on our internal validation set, the F1 score would be slightly better. It's 0.412. So that's kind of the raw performance of our entity linking system. The problem with that approach is that matching of on the surface forms with TF-IDF scores cannot really make use of multilingual aliases in UMLS because they might have just very different surface forms if the aliases are available in English, for example. Therefore, we made use of another candidate generation approach, namely SapBERT. It's a recent development, and that's basically a further pre-training of BERT to make it better at representing relationships in the UMLS. So terms that actually represent the same entity in the UMLS should be closer together. And there's also a cross-lingual version of SapBERT, which allows us to map concepts and aliases in different languages into the same embedding space. And this is exactly what we want to make use of our multilingual aliases in the UMLS dictionary. Once all the embeddings are computed, it's again only a simple k-nearest neighbor search to find the best matching concepts. This approach on the test sets yields an F1 score of, which is slightly better than the TF-IDF scores of 0.369. But if we look closer, we notice that these two candidate generators are actually good at different things. So if the surface forms are very similar, the TF-IDF vectorizer is really good, while the SapBERT candidate generator is better at capturing semantics, but it's often the predictions are more noisy than the TF-IDF scores. So it's a natural idea to combine the predictions with an ensemble and then use the terms that are produced by each candidate generator weighted by an individual weight and applied with a threshold, which yields an F1 score on the test set of 0.425. So it's much better than the two candidate generators alone. Now this approach is not really tailored to the data that we have, and since we know that the actual ranking of the entities, which is relevant because we only look at the top one prediction for this shared task, it also depends a lot on the preferences of the annotators or what was given in the annotation guide. And therefore, the overall ranking in the end is really important. So we implemented a reweighting of the scores by different factors, for example, the semantic type. If we look at the data, we notice that, for example, the semantic type disorder is much more common than morphologic abnormality. We also want to score concepts up where the two candidate generators agree. We might want to score them down if the terms are suppressed in the UMLS, or we might want to score them up if the term is the preferred term for a concept in the UMLS. These different scores or rescorings, reweightings require parameters, and these are tuned on the training data with a Gaussian process. And we use the implementation in weights and biases for Bayesian hyperparameter optimization. And you can see the different combinations of these scores yield to lower or higher F1 scores. This in turn also leads to an improvement of performance, achieving then 0.49 F1 score on the test set. And as a last step, we applied an insight that we got from analyzing errors, namely that the same strings in the training data are always mapped to the same code, and since some terms are quite common in the training data, like lesion, which always says the same concept ID, it makes sense to just reuse that concept ID from the training data. So as a last step, we have an exact lookup for the terms that were already in the training data, and this again also improves performance a lot, achieving then our final score of 0.566. We looked at the performance of the different components more closely, and we saw that actually all of the components contribute to performance, also for different values of k. So for the evaluation in the shared task, we only care about k equals 1. But for other applications, it might be interesting to look at other values of k's, because it might be acceptable to have 2 or 3 or 4 different candidates. So we see that actually all of the additional components actually make the system better. Apart from when looking at the recall, so here we optimize strongly for recall at 1, but we see that for larger values of k, that SapBERT actually improves a lot in recall, and in the end for k equals 10, it's just as good as the complete system. which would lead me to the conclusion that actually using SapBERT as a single candidate generator with a more elaborate re-ranking scheme might yield better performance in the end. So finally, what would be future directions for the work that we did? So with the way we used the training data was in a rather indirect way, I would say. So we used that direct lookup, and we used the training data for hyperparameter optimization, but it might be possible to train machine learning models directly on the annotated entity linking data. For example, it is possible to fine-tune SapBERT on such data. Or there are different rather novel trainable components, such as trainable neural re-rankers or cross-encoders, which might then reuse additional information such as entity descriptions. We haven't looked too much at the impact of the different dictionaries, so it would be interesting to do some ablation studies and to see which subsets of the dictionaries contribute how much to the overall system performance. And our entity linking currently doesn't take into account the context of a mention, which may or may not be helpful for the DisTEMIST dataset. But the overall pipeline is not restricted to DisTEMIST. Many of the components are applicable also in other settings, and we are very interested in applying our solutions in other even less resource domains, for example, German clinical text. To allow such experiments also for everyone else, we made the code open source. It should be able to reproduce all of the numbers that I showed in this presentation using the notebooks that are available in this GitHub repository. With that, I would like to thank you for your attention, and I would really like to hear from you, and would be happy if you reach out to discuss our contribution to the challenge. Thank you so much.